So in the previous lecture, we had looked at using receive signal to estimate distance of a target from the anchor node. Now let's look at a sensing system called radio tomographic that uses a drop or attenuation in the signal strength of the radio signal to enable applications ranging from human vital detection to localization. And best of all, in this localization method, the target does not have to receive or emit any wireless signal. So they are not carrying any active or a passive wireless device that receives or emits wireless signal. And over the next few slides, we are going to discuss this sensing mechanism in detail. And the case study is based on my own research that was published in the conference IPSN in 2015. So let's go and review what is a directional antenna. So a directional antenna radiates or receives greater power in a specific direction. An ESD, or an electronically stable directional antenna, is a type of directional antenna that allows electronic control of the direction of maximum antenna gain. And one example of an ESD antenna is something called SPIDA, which looks like a spider, which you can see on the slide. And these antennas are feasible, simple, and expensive. For example, the SPIDA antenna that you see on the slide can be configured to 6 possible antenna directions in software, and it just costs few US dollars to manufacture. And these antennas are also extremely low power consuming. So by just controlling small RF switch, you can control the direction in which it radiates more or less energy. So one of the methods for sensing and localization that uses radio signal strength is something called radio tomographic imaging. And it enables sensing by looking at the attenuation or the negative change in the strength of the radio signal in a network. And these changes in the strength of the radio signals are caused by the physical obstructions to the radio links. And these physical obstructions cause very unique change in the strength of the radio signals that can help us to perform things like localization or detect human vitals like heartbeat or breathing, or even detect a person, let's say, tripping over and falling. And directional antennas can be very useful for these applications owing to much larger link change or the drop in the signal strength that we observe in radio links when these links are formed using directional antennas and then they are obstructed by a physical object. Furthermore, any obstruction that is outside the area of interest has much less impact on the radio links. So directional antennas are great for radio tomographic imaging. And we precisely use this fact to design a localization system that combines radio tomographic imaging and directional antenna in this work that we presented in IPS in 2015. So just to give a snapshot into the use of directional antennas, here we present one of the preliminary experiments that we did in this study. So the numbers in the heat diagram indicate the location of the wireless nodes. So we have 7 wireless nodes that are distributed in the area. And the heat map indicates the strength of the wireless signal. And the cross is the location of the person. And what we see is that we see a much brighter heat map when we are using directional antenna compared to an omnidirectional antenna. And then, of course, we can extend this to help us localize a person. And this is precisely what we did in this study. So we conducted an experiment and we placed a number of IoT devices or sensor nodes that were wirelessly transmitting packets. And the black circle indicates the location of the sensor node in the experiment setup. And the blue dashed area indicates the ground truth or the path that was traversed by the person. So a person was walking across this blue path, and the red area indicates the estimate that we calculated based on this radio tomographic imaging system. So we compared it against 3 different baseline. So the first 2 were not using directional antennas. The last one, or DRTI, was using directional antenna. And what we find is that the estimate of localization using directional antenna is much closer to the ground truth. So the red contour or the red path is actually what we had estimated using this radio tomographic imaging system. So, of course, the radio tomographic imaging is only just one of the several localization systems that have been developed and now also are in practice that can allow you to sort of like localize person in the environment. So now let's talk about one of the most widely deployed localization system that we also use in our day-to-day life. And this is something called global positioning system. So do you know how this system works? So, so what is a GPS and how does it work? So GPS uses trilateration algorithm, and as you can recall, it requires several different anchor points which are transmitting wireless signals, and then you estimate in some respect by solving several equations the location of the target objects. So in the case of GPS, what are the anchor points? So these are actually satellites, and these satellites for GPS are placed in a medium Earth orbit. And what's the distance at which these satellites are going around the Earth? These satellites are going across 20,000 kilometers, and they orbit twice per day. And they're placed such that there are 4 satellites in view in any place in the Earth at any instance of time. Just to provide context, the International Space Station is located at about height of 340 kilometers. And these GPS satellites are at 20,000 kilometers. And then these wireless signals from GPS satellites are being transmitted from a GPS satellite 20,000 kilometers away, and which can then be received by a GPS receiver that can be located on your, let's say, smartphone. So it's a large distance that is being covered. So how does the 5-layer characteristics of the GPS look like? So typically a GPS signals are transmitted at the frequency band of 1.2 and 1.5 gigahertz. And they take a bandwidth of about 10 to 15 megahertz. And typically these signals at this frequency are not absorbed by the atmosphere. So this allows these signals to traverse a distance of 20,000 kilometers from the satellite to the GPS device with very less or no obstruction. So GPS signals in terms of their modulation scheme use BPSK, which stands for binary phase shift keying. And typically the satellites are transmitting these signals at a transmit power of about 25 watts of 44 dBm. And compare this, for example, to the maximum limit of 4 watts that you can transmit on the ISM or a license-free band. And since the GPS signals are very weak, we are talking about the receive sensitivity or the minimum signal strength that you would want to receive at the GPS receiver to be about minus 140 to minus 160 dBm. And we are talking about data rate of just 50 bits per second. So GPS is a very weak signal at low data rate, but it allows you to perform this localization. And because it's such a weak signal and we are talking about receiving signals at such low sensitivity, GPS actually does not work very well in the indoor environment. And you would have noticed that if you take a smartphone and if it is using GPS to localize, if you take it inside the building, the accuracy might actually fall. And the reason is precisely that what we have talked about. So what kind of transmissions that a GPS satellite sends? It sends a very unique pseudo-random sequence that repeats in time over the duration of minutes. And it is also a very well-known sequence. And then it uses a very similar sequence at the receiver to calculate the time of flight, which we had talked about in the previous lectures. And this helps us to estimate the distance and the location of the target device. So to estimate the distance using the GPS signal, we need to know at least 4 different satellites. So 3 are required for us to estimate the 2D location, and 1 is required to estimate the time offset. And you use all this information to solve an equation that can help us estimate the location and the distance. So how do you estimate this distance more precisely? We initialize the time to one you have heard from the satellite and estimate the time of arrival from the 4 satellites. And now you have 4 variables and 4 equations, and then we solve them to estimate the location. So what are the information that a GPS receiver typically requires? So it is the current time and position of each satellite that is overhead. So how do you estimate the satellite's position? If the GPS receiver listens for up to 30 seconds, it gives the position of a particular satellite from which the GPS receiver is receiving a transmission. And this is also known as ephemeris. And this data typically remains valid for a time of about 4 hours. And after this, the satellite has moved to a sufficient distance and you need to get the new ephemeris data. On the other hand, if the receiver continuously listens for a duration of 12.5 minutes, it can give information about all the overhead satellites. And this data is valid for about 2 weeks and is known as almanac. But also please keep in mind that the reception of signals using GPS receiver is a very power consuming task, as the wireless transceivers are extremely power energy expensive. So if you keep a GPS receiver on for 12.5 minutes just to get this almanac data, it can really drain out the battery of your IoT or a smartphone or other such device. So this process of estimating the satellite location is also sometimes called cold start and can take very significant time as well as energy. So one solution that is applicable to some devices such as a cell phone is that you download this almanac data regarding overhead satellite using the cell phone itself. And this can help you avoid keeping GPS on for a very significant period of time to get the almanac data. And it can allow cell phones to bootstrap the location of the satellite, and then you can get the GPS information for a short period of time to sort of like get the information about your location. So this is GPS. Now let's talk about another localization technique that is called fingerprinting. So what is fingerprinting? It's actually very similar in some respect to what our fingerprints are, that it sort of like gives you a unique information about a person with that fingerprint. So this technique is based on the concept of repurposing and reusing existing wireless infrastructure to support localization. As an example, Wi-Fi access points are very ubiquitous. So you just go around your building and you'll find that there are lots of Wi-Fi access points that are deployed. And these are typically deployed at fixed locations, and you don't typically move these access points around too much. So if we can somehow use them to help us estimate the location of the device that is connecting to the access point, that could be a very scalable solution to support localization, especially in an indoor environment. So as an example, if we walk around the campus, there are access points in known places. We can locate with their names accordingly, and a smartphone can connect and sort of get a rough idea that, okay, I am at location A or B. And in fact, what do we do next? We can also, we can have sort of like a setup phase where we may estimate the strength of the wireless signal from the access point as you actually traverse distance. So let's say you are at a 5 meter, 10 meter, 15 meter distance, you can estimate roughly what would be the strength of the wireless signal if your device connects to this access point. And we can create a sort of like a database that stores the name of the access point, the distance, and the signal strength from the access point. And sort of like have this data. Next, what happens is that when you have a device such as smartphone that connects to this access point, we can query this database and the signal strength to give us some estimate for the location of the phone from this access point. So we, for example, just show a distribution of signal strength for one scenario in the slide. So the star indicates the location of the access point, and the red means that the signal strength is higher, and the blue, the signal strength is weaker. And we can sort of build on this concept to allow you to localize, and this method is called fingerprinting. So how can we improve the fingerprint accuracy? We can maybe make a database from several access points. So we can start to use several access points, have each database, and then combine this information from several access points to get better accuracy in terms of the location of the target object or person. Another thing we should keep in mind is that fingerprint is a generic technique, and it is not only specific to Wi-Fi, but can also be applied to other technologies such as cellular networks. So you have cellular towers, and you could sort of like figure out the distance from this tower and get some estimate for your location. Or even, for example, we can start to use technologies such as Bluetooth advertisements or Bluetooth. So the actual deployment and the technology would very much again depend upon the application requirement and the other specific constraints. So what are the challenges with fingerprinting technique? It may take a significant effort to create a database in the first place. It would require taking measurement at every location and also then updating the database. So it can be actually very time consuming and expensive operation. Furthermore, the signal strength can vary a lot as we change the environment, or there are environmental dynamics. This would require periodic measurements and ability to update the database, and this may turn out to be a very expensive task. And finally, RSSI measurements can vary with two devices or even with the orientation of one device. And I will actually suggest you to do that for the particular assignment where you're calculating RSSI, to just look at how the RSSI varies when you change the orientation. And this could also lead to errors, which are something we talk about next. So what is the typical accuracy of fingerprinting techniques? It is between 0.5 to 1.5 meters. So it's not highly accurate. You will probably not use fingerprinting to localize things like drones. However, this can be used for many other applications where high accuracy is not required. So it's one of the techniques which has some overhead, but there is also some inherent simplicity from the receiver side, that you're just estimating the strength of the signal and sort of like finding what's the name of the access point to get you some information about your location. So with this, we conclude this part of the lecture. Thank you.